we're gonna like press pause on the warm up for a second, okay? And then we'll return to this problem. I'll let you do the warm up in like, 3 minutes from now. I want to say a couple things about two of the slides we didn't get to yesterday, which hopefully, like I said, you looked it up in the book maybe, who knows, whatever, you figured it out. If there are a couple problems like you needed to know a couple of these things to do. So maybe this will answer some of your homework questions as well. So we're going to take like a minute of notes, and then I'll let you get back to the warm-up. So the first thing I want to introduce is the idea of a unit vector. And a unit vector is not like a rocket science name for it. It's just a vector that's 1 unit long. Right? So it might not even seem like a concept that's worth mentioning or having a name or worth talking about, but it is. And you'll see why it's really useful as you move forward, both in this class and into the future, as you eventually someday take a linear algebra course. You'll realize that unit vectors are like master of all. So if we want to get a vector that we have in our possession and make it 1 unit long, then all you have to do is divide by the magnitude. Right? That's like a scalar operation on the vector. By dividing by a number. Okay. I thought class started already, but that's right. I have a couple bells just to be sure. When you divide by a number, remember that's a form of scalar multiplication. And whenever we're multiplying by a scalar, we lengthen the vector, or possibly shorten the vector, right? Depending on whether that number is greater than or less than 1. We can make a vector longer or shorter by multiplying by a number. So that's what this does in particular. And still in the same direction, just has a magnitude of 1 now. So, for example, if you wanted to do that to this vector, -5, 12, and by the way, I've just chosen to write it in one more way that people represent vectors. There are like lots of ways people like to write vectors. Vectors are such an important idea, so of course there are lots of ways to write them. That's what happens, I guess. This is in particular IB's favorite way of writing vectors. They will often give you a column vector like this. Okay? Find the unit vector in the direction of -5, 12. That is to say, give me a vector that still points in the exact same direction as this vector, but is only 1 unit long. So, yeah. Yeah, those are parentheses. It's like a... But there's nothing wrong with having them. Sometimes you'll see it written with brackets, like a matrix, too. All of this is like stylistic considerations. Sometimes you'll see a vector written that way as well. All of its style choice. An ordered pair, whatever.
Oh wait, so it's like also the 5, 12 thing?
Yeah, it's also -5, 12.
Wow, that's cool.
Yeah, it's all different ways of writing. The reason why you might like this way is if you multiply this by a 2 by 2 matrix, it transforms this point into another point, and that's how you might think about it in like a linear algebra course. So anyway, a vector you could think of as like being a column matrix, All right, anyway, whatever. We've gotten too far afield. How do we make this unit 1 unit long? How do we make this, which is currently how long?
13.
Yeah, picked some nice numbers there, right, didn't I? So, does everyone see that? Or if you're not sure, actually do the magnitude. What is the magnitude of that vector? It's the square root of 5 squared plus 12 squared. And work it out. You'll get 13, but I picked one that works out nicely, didn't I? So yeah, the magnitude is 13. So actually, maybe I can just write down the answer. If it's currently 13 units long, and I want to multiply by something that makes it 1 unit long, that thing I might want to multiply by is maybe 1/13, right? Like I want to make it 1/13 as long as it is right now. So we could like say more or write more, but I think we can maybe just write this down. It's -5 over 13, 12 over 13. Certainly it's still in the same direction, right? Because all we did was multiply by a scalar. All we did was multiply by a number, 1/13. So it still points in exactly the same direction, and yet it's only 1 unit long. If you don't believe us that it is 1 unit long, you can check the magnitude of our new vector, right? The square root of -5 13th squared plus 12 13th squared, and see that it's 1, right? It'll come out to be 1. So I think we did it. There are 2 important unit vectors that you see in the warm-up as well that we want to say something about. 2 nice unit vectors are these 2 unit vectors. They're certainly 1 unit long, and they're the unit vectors that point in the directions of the positive x-axis and the positive y-axis. And they're so important that we give them names, I and j. And that's just not like our names. That's like universal in mathematics. People will know what you mean when you talk about the vectors I and j. And soon we'll do some vector stuff in 3 dimensions, and we'll add a third unit vector, k, we'll call it, and it'll be in the direction of the z-axis. So that might seem like a really kind of dumb idea, like why do we need to name these? But it's actually kind of a powerful idea. The fact that we can write any vector of your choice in terms of these two vectors. So I want to make sure you understand by by bold I and bold j, I mean the vectors I and j. So like on the warm-up today, I think it's 5i minus 9j or something like that. Why is that a vector? Well, it has a plus in there. Why is that a vector? Well, because I and j are vectors. They're 5 times the vector I plus 9 times the vector j. Together gives us another new vector, namely, it's not very interesting, it's just 5 comma negative 9, right? But it's still a very powerful idea that the fact that we can like take two little vectors, as innocent as they might seem, and build every other two-dimensional vector that exists using what's called a linear combination, right? By mixing the two in different proportions, we can create any other vector we like. You might ask, can you do that with other vectors? Like, could I take these two vectors that are not 1 unit long? Could I take these two vectors and use those two vectors to create all other vectors? That's like a really interesting discussion, isn't it? You should take linear algebra someday if you really want to plumb the depths of that question. Okay. So all right, that's all I wanted to say. Let's return to the warm-up. I'm going to come around and check the homework, and then we'll continue talking. We do have a lot to get to today about applications in a minute, okay? It could be 200, like, or what do we say, 299.9 or something? Or 200, 300 degrees if we're doing 3 sig figs. 300 degrees would be a good answer, too.
Yeah, but like, minus
Well, you definitely need, whatever angle it is definitely an angle that terminates in the 4th quadrant, right? Because like, look at the vector. It's 5 comma negative 9. So maybe you used an inverse trig function that left you in the 1st quadrant, but you need to then adjust in a way that you know how, right? Like you know better than your calculator maybe. Or for those who got this answer directly, you probably used inverse sine or inverse tangent or something, right? Okay. All right. So I don't have anything else to say about that. Was there, I'm trying to think if there's something else in the homework that was cut up. The one thing in the homework that came up that maybe that people were asking about is the unit vector in the direction of like another vector or something like that. Is that what you want to look at?
Yeah.
I think it was 39 that asks you to create a vector of length 2 in the direction 3, negative 3 or something like that. Okay, so the point is like this vector, we don't care how long it is actually. We'd like to change it and make it 2 units long. So right now, how long is this vector? 3 comma negative 3. It's 3 root 2 units long, right? So could we make this 1 unit long? Yeah, in the way that we just described a second ago, right? We could divide this by the magnitude of this vector, which is 3 root 2, right? And when we do that, we get a new vector that's still in the same direction as this vector, because all we did was multiply by a scalar. So here's the vector in the direction of this original vector here, but only 1 unit long. So what we've essentially done when we make a unit vector in the direction of this vector is we've kind of like taken it and stolen the direction information and like stripped it of its magnitude information, right? It's like now it's exactly 1 unit long, okay, in this direction. Now what if we wanted this, though, to be instead 2 units long? Just multiply it by 2, or any other length that you'd like it to be, right? Does that make sense? So there it is, and when you multiply this in, you get what? 2 over root 2, comma, oh my, comma, negative 2 over root 2, or if you prefer, it might look nicer, what is that, root 2, comma, negative root 2, right, would be a good way to write. So that's going to be, the reason I highlight that is that will come back to be useful later in your life, so I want to make sure I highlight that problem, yeah.
So this was probably excessively long, but the way I did it was I found the direction, and then I plugged in the value in cosine.
Oh, yeah, yeah.
So that also,
You should get the same answer, right? Did you get root 2, comma, negative root 2? Yeah. Isabel?
So when they say in the direction of a vector, that's in the same direction?
Right. Right. It means we care about the direction, but we don't really care about the length of that vector. Yeah. Okay. So we're gonna turn our attention to applications today, still in the same section, but we want to like say a couple reasons why we can use vectors for some use here. And our notes today consist of just a couple examples to go through. There's no like additional theory to build up or any theorems to provide to you or anything like that. So let's just jump right in and try a couple of these problems that cause us to think about vectors in the real world. Eric, would you read the first one for us about the tank?
The tank on a mission produces a velocity of 27
Hey,
miles
guys.
per hour with a bearing of 161 degrees. Find the component form of its velocity.
Okay, so I think that maybe there was a time last semester where we came up against the word bearing, but maybe not. Let's describe again what that is, maybe, or maybe it's the first time ever talking about it. So in mathematics world, among us as mathematicians, we really like measuring angles in standard position. That is, from the positive x-axis, measured counterclockwise in the positive sense. Right? That's how we like as mathematicians to do it. But in the real world, if you're like an orienteer or a navigator or something, you're on a boat or a tank or I don't know, whatever. If you're like someone who is doing navigation, you might use bearing. Maybe this is something you've heard before outside of mathematics. So by bearing of 161 degrees, maybe I should even say this. We mean measured from north. Okay? And furthermore, to make things even more complicated, it's measured clockwise from north. Okay? So this is how, like, if you're ever doing navigation or something like that, I guess that's how they do it, right? So here's north, and we're measuring, so this tank, we mean it's headed in this direction. 161 degrees from north. That is from north, measured clockwise, 161 degrees. So this is the direction in which the tank is going. And the length of this red directed line segment is 27 units. Well, how about 27 miles per hour long? I know that's a weird, that's what I said. It's like the magnitude we're going to represent as the length of the vector. Seems a little weird to like call that vector 27 miles per hour long, but that's how we want to kind of think of the length of that vector as representing that. So that's 161 degrees from north. That's one way to say it. We might also prefer to use our own mathematical language. We might say that that angle in our normal way of saying it is negative something, what is it? 71 degrees? Sorry, not to scale. Does not look like 71 degrees. Okay. Yeah? That makes sense? Okay, so what are we supposed to do? Find the components of the velocity. So first of all, let's recognize that that is in fact what's given. We're given a velocity, both the magnitude and direction. So we talked about that a little bit yesterday, the nuance there. We're talking about a velocity. It has two parts to it, right? It's a two-dimensional quantity. So we can write down the components of this. How do we find the components of a vector? If we know the magnitude and the direction. We use the trig, right?
27 cosine negative 71 would be x squared.
Yeah, we're trying to find like this piece and this piece, right? Trying to break this down into its two components. We need a horizontal component and a vertical component. And even though this seems like, oh, whoa, new context, new problem, crazy tank situation, it's still the exact same thing we said yesterday. It's still magnitude times the cosine, comma, magnitude times the sine, right? So 27 cosine negative 71, comma, 27 sine 71, negative 71. And then I guess we can approximate what that is, but then that's all this is asking for here. Yeah, Eric.
So the magnitude is 27.
Yeah.
So like,
Right.
you did in like miles per hour.
Yeah, so exactly. So I know that won't, like I said, I said that might not sit well with you to like think of a line segment as having a length of 27 miles per hour. That's why we prefer the word magnitude. But yeah, later we're gonna also like talk about, you know, we have some, even in this paper, we'll have like some thing that we're applying forces to, and we'll like represent it this way, right? We'll like say, here's a force acting in this direction, here's another force acting in this direction, and this force is bigger, so we're gonna like draw a longer line, directed line segment. Does that make sense? Is that a good way of capturing both the direction information for the force and also the magnitude of the force, right? If you have like two people fighting against something, you might want to represent their forces having a longer arrow, right? Same thing, velocity. Like we have two things that are moving in space. We're going to use a longer line segment to represent something that's moving faster in that particular direction. So both the line segment's length and its direction matter to us in the interpretation, right? So yeah, you just kind of have to get over the fact that like it's weird that it's measured in miles per hour or something. Yeah. Go ahead, Jim.
So when you're writing the 27 cosine of negative 71 degrees, what do you write 27 miles per hour cosine? Or is that
Yeah, it is actually 8.79 miles per hour in the x direction.
Yeah, but are you supposed to rate it when you're writing like
Yeah, I mean technically, I don't know if I would take off for it necessarily, but technically, yeah.
And the other one is, you wouldn't rate something like bearing and expect us to know that. Normal.
I would expect you to know what bearing is on a test. Yeah.
You would?
Yeah. Yeah, you'll see it all over the place in the homework tonight too. And so yeah, let's get used to understanding what bearing is. And going from bearing, like in this, just like in this problem, to a normal angle that we might know and love. All right. Okay, let's hear from Grace. Are you want to do it? Where are you, Grace? Oh, are you Grace too? Do we have more than one Grace? Two Graces. I actually pulled you though, Grace. But I'm glad I know that. There's two Graces. Would you read the next one?
An airplane is set on a course with a bearing of 352 degrees at 290 miles per hour. The wind is blowing at 300 degrees at 46 miles per hour. What is the actual velocity of the airplane?
Okay, so you understand the question here maybe. We've got an airplane and a wind, and one affects the other in a way that you maybe are even familiar with. So the first thing I might try and do is draw this, and then we'll try and figure out what might be asked of us here. So I'm going to draw the airplane's vector in blue. I'll try to make this obvious. It's got a bearing of 352 degrees, again, from north, measured clockwise. So how does that look? Measured north. So where are we? Yeah, almost all the way back to north. In fact, maybe people in the real world might say also, instead of saying it this way, they might say 8 degrees west of north, they might say too, would be another great way to say this. But yeah, we're right here. Are we all convinced that we're right here? So there's a blue vector representing the airplane. And let's just say right now, what is that angle in standard position? 98 degrees in standard position, right? Because it's 8 degrees. We almost made it all the way around except for 8 degrees. So there's 90 degrees over here plus 8 degrees if we're measuring it in like our normal way. Good, and it's, again, I know this doesn't settle well with you, but it's 290 miles per hour long. Sure, ooh, yeah, okay, we'll go with it.
So could we always just change it to 98 miles? 98.
Yeah, right away, because that's the way I'm going to want to see it probably as a mathematician. Yeah, exactly. And then we're looking at a wind. Let's see if we can represent that in a way that's nice. And with red here, let's also draw that vector. We've got kind of two vectors at play here. It's blowing at 300 degrees. Where is that? So that's like almost all the way around 60 short of where we need to be.
It doesn't say bearing, so we assume it's bearing.
Yeah, let's assume it's bearing. Sorry, maybe I should have said that. My bad. Okay. At 46 miles per hour. So I'm like, this is definitely not to scale. But I am trying in at least some measure to show that it's not as big of a velocity. Yeah? Again, this comes into play, like the length means something to us? Yes, it does. And what's the angle there then?
That is 150.
60 plus 90? 60 in here and 90 there. 150? Okay. Good. All right, now we need to like step back and have a little bit of a discussion. Say you are inside of a bus going 70 miles per hour on the highway or something like that. and you throw to the person in front of you, you throw a ball at 10 miles an hour. This is like the classic example, right? If you are inside the bus, we've got like this beautiful inertial frame of reference here. Throw it forward at 10 miles an hour. How fast does the ball travel with respect to the road?
The speed of the bus plus the speed.
Yeah, it's the speed of the bus plus the speed of the ball. It's actually traveling with respect to the road.
Direction respect.
Yeah, there's also some Einsteinian stuff happening. It goes 80 miles per hour, right? With respect to the road, okay? Does that make sense? Maybe you've never thought about that. Or if you throw it to the person behind you, right, at 10 miles an hour, it's going, if the bus is, again, let's say the bus is going 70 miles an hour, then it's going 60 miles an hour forward, even though you threw it backward, it's going 60 miles an hour forward with respect to the road, right? Have you ever thought about this? Such a wonderful thing to think about. Hey, it's such a wonderful thing to think about, because next time you're driving in a car on the highway, especially, you're thinking about how fast you're going. And notice that, like, you, as you're going forward, if you're going at a constant velocity on the highway and you're not making any turns, you're going straight. Thanks, guys. I know this is hard to think about. Hey, guys, can you be with me here? If you're traveling in your car at 60 miles an hour or something on the Beltway, and you're going straight, it doesn't feel like, if you're maintaining a constant velocity, it doesn't feel like you're going anywhere. If you just like were to throw an object, try this sometime, right? And think this, I love thinking about this as I'm in a car too, or in an airplane especially, if you're going 400 miles an hour above the earth. If you're just like to flip your pencil in the car, it works great. And relative to the car, the motion of the pencil just looks like that, right? But, can you imagine, like, maybe picturing video replay of the pen's travel if you like remove the car from the scene over the top of the highway? Just in that like 2 seconds that you flip the pen, with respect to the car, it looks like this. But with respect to the road, it's like, right? It would be really cool. It would be fun to see, wouldn't it? Can you imagine that? Imagine that next time you're like up in an airplane and you're like walking to the front of the cabin or something like that. Oh, I'm actually walking with respect to the earth. I'm having myself like a 400-mile-an-hour walk. You know what I mean? Like, because with respect to the earth, you're like actually, you're just taking a stroll, but with respect to the earth, you're like, you know, it's cool. So think about that. All right. With that in mind, that's the one-dimensional thing that's happening. So my question would be, okay, I think I get this now. How much velocity, let's just think about the x direction. How much velocity do we have if we're on this airplane? We got the airplane being kind of aided along by the wind here. We have this much velocity contributed in the x direction, right here, from the wind, and then we have this much sorry, this is again not to scale really, so this is not too good. And we have this much velocity, the x component of this, from the airplane. And when we add those together, just like we just did now, we get the total x velocity, the velocity in the x direction for the actual motion of the plane. And we can do the same kind of argument in the y direction, right? We have this much velocity in the y direction, and this much velocity in the y direction for the wind and for the airplane. And it's exactly the same situation if you're convinced about our little bus throwing ball example. It's exactly the same situation, but just done in 2 dimensions now. And we're going to add the amount of velocity in the x direction together. We're going to also do that in the y direction also now. Before it was just 1 dimension, but now we're going to do it in both dimensions. So hopefully we've successfully convinced you that we're going to be adding these 2 vectors together component-wise, okay? Which results in a vector that looks like this from yesterday we talked about, right? We get this like resultant vector, the sum of the 2 vectors, right? Which is the actual path of the plane then. So we're going to add those together and get that resultant vector. So in blue, we've got the airplane. Airplane, here we go. Just like on the last example, it'll be the component form for the blue airplane vector is 290 cosine 98, 290 sine 98. And now we've got the wind vector in red. Wind, here we go. What is that? 46 cosine 150, 46 sine 150, And then we're going to add them. So go ahead and do that. You can beat me to it. When you get the answers, though, please store them in your calculator in letters A and B. You ever had to store variables?
Why not A and W?
Or A and whatever you like. No. I meant the answers down here we're going to store in 2 letters here, okay? So this will be our resultant vector in its component form. I've got my calculator here too, so I'll do this. 290 cosine 98 plus 46 cosine 150. Store in. So I get negative 88 point something, negative 88.858. So. And. Oh no. Nope, I can't talk now. Okay. And 315.1777 or something like that. Okay. So that's the component form. Yeah. All right. So there it is in component form. Did I? 56. What? Not 46.
Yeah.
I see. I know. Charlotte. That's what you're saying. I know.
It's a different character.
Yeah, it is.
Okay.
I mistyped. How about 310? Does that sound better?
Yeah.
And what is? Negative 80.197. Check me on those again. All right, so store those. I stored those. Personally, you can store them in any letters you like, but I stored them on my calculator in letters A and B. So find, now, if the question was asked this way, you probably, if you're like going to give the pilot information, you probably are not going to give them back like the component form of the velocity. It's like not that useful to him. He probably would like to know, so how fast am I going? Like what's my speed and maybe what's my bearing? He'd like to maybe know those things. So let's give them back to him that way. The magnitude, now that we have A and B stored in our calculator, can be computed as A squared plus B squared, take the square root. So I'm doing that right now. And I'm getting 320.378 miles per hour, okay? And the angle, too, we need to think about the angle as well. Well, how do we do that? By the way, do we have this in the right quadrant? Like we have, it's definitely negative something negative, comma, something positive. So we're in this green vector. It does look right too, intuitively. I think I like it. Yeah, we're definitely in the end gonna, when we box our answer, we're gonna write everything in 3 sig figs. So how do we find that angle? Do you have it?
Is it just tangent theta equals b over a, and then it's just
Yeah, you could do tan. The only issue with tan inverse on your calculator is what though?
it gets in restricted.
Yeah, it won't give you a second quadrant angle. So I might reach for. I mean, you can do whatever you like though.
Like what I usually do is like that to make a reference angle and then subtract it from my maybe.
There you go. That's fine. Yeah, absolutely. Get the wrong angle and then fix it. Whatever. Any correct method is fine with me. Doesn't matter. But you're certainly welcome to use which one would get to you directly. Yeah, cosine inverse would give it to you right away if you want. So theta. Now keep in mind this is not the bearing, but we can get theta right away. It's cosine inverse of a, that value negative 80 over 320. Use the full value though, right? So I'm going to type that in here. A over answer. Yeah.
Is there a reason why like all the answers have different sig figs?
In the end, I haven't boxed anything yet. I'm being kind of cavalier.
So like in the calculation, or are we just using the calculation?
I'm using the full value. There's never, like, the thing I just typed in is cosine inverse of A divided by ants, right?
Ants?
Like the previous answer that I got.
I prefer ants, like the bugs.
Yeah. So that is to say, there's never a time ever in your life where you should use a rounded value in a calculation. If that hasn't been made clear to you yet, we gotta hammer that into your head. Okay. So disregard any sig figs until I put it in a box, and then I'll put the correct 3 sig fig answer in a box at the end. All right. So what I get? 104. What you got? 0.49. 65. You can have some more if you like. Whatever you like. Okay, and then that's not bearing though. How do we get back to bearing? That's 104 degrees. Maybe my intuition here is we like subtract 90 to figure out what, just like the reverse of what we did before, right? So that's 14 degrees in here, 14.49 degrees. And then we subtract that from 360. I don't know. I'm getting 345.5, right? So, all right, so here's my final answer. 320 miles per hour, 3 sig figs, at a bearing of 345 degrees from north. 346. It's a little closer to 346. There we go. Yeah. So I did a little bit of geometry, like we kind of just went fast and loose on that on the front end. So you could probably come up with like an algorithm for taking one to the other, but I'd probably just prefer to use geometry and look at the picture. So this is 104 degrees. I think that makes sense from the picture. And then how do I get the bearing? Well, the bearing is this angle, measured clockwise from north. Okay, with that information, like just go, figure it out, geometry-wise, right? Can you do it? Do you understand what I did?
Yeah.
What did I do? I subtracted 90, figured out what this sliver was, and then subtracted that from 360 is what I did. That's probably not actually the most efficient way. It's just the way I first thought to do it, right? Whatever. Yeah.
So the big one on 346, that just means bearing.
Yeah, I said from north. Yeah, exactly. Sorry. You could just say 346 degrees, and I guess we'll know bearing. 346 degrees measured from north, clockwise. Yeah. One other thing I should say about this problem is there is another way to solve this problem, and that's this, okay? I just want to show you. One other way to represent these vectors instead of like this, like we represented them, would be end to end. And I think you would all agree that we definitely do still get the same picture here. You know, the resultant vector that we care about is still this one right here. But notice what you see here, especially once you let the coordinate plane drop away in your mind's eye. What do you see? You see a triangle, don't you? And it's a triangle that you know the side length here in miles per hour. You know the side length here, and it wouldn't be very hard to compute that angle. Could you compute the length of this side using, oh, I don't know, law of cosines maybe? If you know two sides and the included angle, could you find the length of the opposite side? That would be the magnitude. Boom, done. Could you find, you still need to know the angle, right? So how would we get this angle? Well, this angle is given, this first little one, this big one here. This angle you'd still have to find, but again, that would be you solving for that angle in this triangle. So you could reduce, the point is, you could reduce this if you love triangle solving, you could reduce this all to just like a triangle solving problem too, if you're in love with triangle solving from last semester, right? Okay? And just, you know, it might be kind of a fun activity for you to try that and just verify that, in fact, you do still get the same answers we just got, okay? I'm not going to work through that. I just wanted to say that that's fine, and you can do that. All right, can we read the next example? Maybe Justin, are you willing to read about llamas? Listen, please, guys.
Two cowboys have wrangled a wild llama. One pulls on the llama at 21 degrees with a force of 20 newtons. The other pulls at 17 degrees with a force of 30 newtons. See diagram. Despite all their pulling, the llama holds her ground. What is the magnitude force of her resistance? The magnitude of her resistance.
Okay, yeah, so, and the diagram really is necessary here. The question isn't clear enough to maybe make it obvious, so go with the diagram. We've arbitrarily put an x-axis in here, kind of, right? So go with it. And we have two cowboys. It's like we're replacing them both with one big cowboy. And by the way, no bearings here. What would the overall magnitude of the force that the two cowboys together are applying? Well, it would be 20 cosine 21 plus 30 cosine negative 17. That would be one component of the force. And over here, 20 sine 21. And what is this, 30? Sine negative 17. Add those together. And then, just because I want to give you about a minute here, so let me tell you something, the setup here. Once you get that, you'll have the total force applied together of both of them. Now, what would it be? What would have to be true? And it turns out to be 40. The magnitude is 46.4 newtons. Turns out. Okay. So what would have to be true if that's the total force that they're applying together? What must be true if the llama is staying still that it's doing? Yeah, I mean, you don't have to even know Newton's laws to know that it is going to have to be applying an equal and opposite force, right? So if it's going to be standing still, I guess it's also applying a force of 46.4 newtons in the opposite direction in order to stay still. So that's the final answer on that one. If you want to check me on it, do the work here.
Yeah, we got 47. Yeah, I got 47.
I'm going off the top of my head. Some people are saying it's 47.4.
I don't know.
Huh?
I
I'm just like going off my memory here, okay?
I think I'm probably wrong, but I think if you subtract the standard position angle from 450, like it's still.
I have to think about that. All right, bye guys.